Today we're going to finish up our last part of our last unit for this course. So we're going to talk about finding the volume of a solid of revolution using what we call cylindrical shells. And so I've kind of got a few steps here, some guidelines to follow as you're going through and trying to find the volumes. And we're going to talk as we go through a little picture here. We're going to kind of talk about what each of these steps is, and we're going to talk about why this method is actually quite useful sometimes. So what we're going to do is we're just going to start with a real basic drawing here. So I'm going to just kind of sketch. Let's say I had the region right here, right, bounded by some parabola and some horizontal line. And so let's say we're going to take that region and we're going to revolve it around the y-axis. So I'd end up with something that kind of looked like, like this, like bottom half of an A corner, something like that. And we're going to see if we can figure out a method to find the volume of it in a different way than using disks, right? Because we could slice this thing into an infinite number of little infinitely thin horizontal slices and do this in terms of y. But we're going to see if we can find a way to think about this region in a different, or think about the solid in a different way. That's going to allow us to do this in terms of x. And so what I've done here is I've done step one, actually, is I've graphed the region. And what I'm going to do is draw what we call a typical rectangle that is parallel to the axis we're revolving around. So I'm going to draw a rectangle that is infinitely thin in the x direction that is parallel to the y-axis, since that's the axis that I said we're going to revolve around here. And then I'm going to sketch a shell. So here is how I'm going to sketch that shell. And we're talking about this as if we took that infinitely thin rectangle and revolved it around the y-axis, leaving us effectively with a hollow cylindrical shell. Basically, you can think about it like it's like the end of a roll of toilet paper, right? You've just got that little cardboard tube that's really thin, and it's the hollow cylinder. And so we're going to think about this problem as if we have an infinite number of these little rectangles, all with an infinite thinness of dx that are being revolved around here. And so I've drawn a narrower one inside of there. And I could draw, let's say, one that's a little bit shorter, right, but that revolves further around here. And it's just, they're all just a bunch of hollow tubes. And they all sort of fit inside of each other. So you can think about, like, let's say that green one was all the way up against the y-axis almost, and infinitely thin there. Then there'd be another one that was right on the outside of that one. So they fit perfectly inside of each other, except the taller ones would obviously be sticking out the ends, like the green one, and the red one would be inside of the outside of it, but sort of shorter than it. And the blue one would be outside of the red one, but shorter than it as well, all the way up the line until we got to the top region, where we have a really short one here that went almost all the way to the outside edges of that region. They kind of fit together. The good analogy for this is like Russian nesting dolls, like where you pop the top off of one of them, there's another doll right inside, and then you open that one up and there's another one inside of that. They kind of fit together like that. And together, this will take up all of the volume of this solid that we would get by revolving the region around the y-axis. And so what we've done here is we've actually sketched more than one shell, but we really only need to sketch one. We've determined our thickness here, right? Each of these is going to be a thickness of dx, which is going to allow us to do this problem in terms of x, right? Which is very different than if we tried to do it using disks, right? If we did this using disks, we could do it, but we do it in terms of y. This will allow us to do it in terms of x. So that's the cool thing about cylindrical shells, is they'll always end up being in the opposite variable as if you were doing disks and washers. Right? And we'll note that this is we'll put that in here. This is the opposite variable of disks or washers, which is really convenient because there will certainly be some instances here where it'll be impossible for us to use one variable. So we'll have to switch to the other one. So sometimes it might be impossible to use a disk or a washer. And so instead of sitting there with no idea what to do, we'll be able to use these cylindrical shells. So what we then need to think about is how do we find the volume of a hollow cylinder? Well, the volume of it would be the lateral surface area. Lateral surface area being just the section going around. Right, that'd be the lateral surface area. And then if we multiply it by the thickness of that shell, which is infinitely thin, in this case in the x direction, that should give us the volume of it. So in order to find that lateral surface area, we need the circumference up here at the top, and then we'll multiply it by height. So the lateral surface area is 2 pi r times the height, and we'll multiply that by our thickness of dx. And then all we'll need to do is pop that into an integral and integrate, in this case, from the left to the right bounds of the region, since we're doing it in terms of x, and we'll get our answer. So that'll be our next steps, is find the radius, find the height, and then our surface area will be 2 pi rh. We'll multiply it by our thickness dx, or sometimes we'll have dy, and then we'll use an integral to sum them together. So that's the idea of cylindrical shells. So let's see if we can put this into practice. We're going to start with y equals the square root of x. So we're going to take y equals root x, and we're going to take the line x equals 4, and we're going to take the x-axis. So we're talking about this region right here, and we're going to revolve it around the x-axis. Now, obviously, revolving that around the x-axis, right, we're going to get something down here. We could slice that perfectly vertically into an infinite number of little slices and do it in terms of x, and it'd actually be a really straightforward problem. But just for the purposes here of learning how shells work, we're going to see if we can find a way to set this up using cylindrical shells. So we've got our region sketched, and then the next thing we were supposed to do is draw a rectangle that stretches across the region that is infinitely thin in one direction and is parallel to the axis we're revolving around, so parallel to the x-axis. And so this thing will be thin in the y direction, which means that we're going to do this problem all in terms of y, which is completely different than if we were trying to use the disk method. The disk method, we were slicing this direction, making it dx. But now this will allow us to do it in terms of y. So we'll sketch that shell going around here. Okay? And all we need to do is 2 pi times an integral from the lower bound of our region, since we're doing this in terms of y, so 0, to the upper bound of our region. So if x is 4, y would have to be 2. Right? So we'll do 2 pi times the integral from 0 to 2. And then we're going to do the radius and the height. And so our height is just going to be the distance from the function here to the right bound of our region there at x equals 4. Right? That's going to be our height. And our radius is just going to be the distance from that rectangle, right, that we've gone around, which is really just the height of our function, to the x-axis. So our height is just going to be y, which is great because we need to do this in terms of y. And our radius, right, our radius is just going to be, well, I don't know why I said our height. Our radius is just going to be y, and because this is our radius right here. Our height there is just going to be the full distance from 0 to 4 minus x. So our height is going to be 4 minus x. And since we're doing this in terms of y, we'll need to note that x is equal to y squared. So our height will be 4 minus y squared. So our radius here of our cylinder is just y, and that will always be the case when you're going to be revolving around the x-axis. Right? Your radius should always be y. If you're revolving around the y-axis, your radius should always be x. And so all we're looking at here now is 2 pi times our integral from 0 to 2 of our radius times our height, dy. And obviously, we could distribute that out, but just like last time, we're just focused mostly on setting up the integral. That's a pretty straightforward power rule integral that we don't really need to go through anymore. So there's our first shells problem. So let's take a look at this next one here. This time, we're going to take the region in the first quadrant that is bounded by y equals 4 minus x squared, y equals 3x, and the line x equals 0, x equals 0 just being our y-axis. So we're going to talk about this region right here. And what we're going to do is we're going to revolve that around the y-axis. So our first step here, once we've got the region graph, is to sketch a rectangle that is parallel to the axis we're revolving around, and that is infinitely thin in the opposite direction. So this will be not dy, this will be dx, right? Because it's infinitely thin in the x direction. If we were trying to revolve this around and do discs or washers, we'd have to slice it horizontally, which would give us dy. And so this is going to allow us to do this problem in terms of x. So we're going to start our integral off with a 2 pi, and we know we're going to integrate from the left bound of our region to the right bound of our region, which is going to be 0 for the left bound. But to find the right bound of our region, we're going to have to set 4 minus x squared equal to 3x. So we'll end up with x squared plus 3x minus 4 is equal to 0. And then we'll just factor that into x plus 4 and x minus 1, giving us intersection points there of x equals -4 and x equals 1. And obviously, x equals -4 is going to be this one over here where they intersect. This one here is going to be x equals 1. So you do need to show that work when you're showing your work on my test and the AP test of how you found the intersection point. So our x value there is going to be 1. So we're going to do 2 pi times integral from 0 to 1 of our radius. Well, our radius is just the distance from the axis we're revolving around to our rectangle, which is just a horizontal distance from the y-axis, which is just x. So our radius is just going to be x. But our height extends from the upper bound of our region to the lower bound of our region. So if our radius is x, our height should just be the vertical distance between the two functions. And the vertical distance between two functions is always just the upper function, 4 minus x squared, and then minus the lower function, which is just 3x. So our integral here should be x, our radius, times our height, 4 minus x squared minus 3x dx. And that is our setup here, allowing us to do this problem in terms of x instead of in terms of y, as if it was a disk problem. All right, so for this next one here, we're going to, again, use shells. We're going to take the region that involves y equals root x, y equals 2x minus 1, and y equals 0. Y equals 0 is just our x-axis here. So we're talking about this region right here. And we're going to revolve it around the line y equals -2. And so y equals -2 is somewhere down here below where the 2x minus 1 hits the y-axis. And so we're going to first then sketch a rectangle that is parallel to the axis we're revolving around. We'll note that it is infinitely thin in the y direction. Right? It's very thin in the y direction. So this will become 2 pi times an integral from the lower bound, 0, of our region to the upper bound up here. And so we'll have to set root x equal to 2x minus 1. With any luck, you just kind of real quickly see that that's just x equals 1, just by like kind of thinking about what the value might be, right? The square root of 1 is 1, and 2 times 1 minus 1 is also 1. But if you had to, you could square both sides, then it'd turn into a quadratic, and you would solve the quadratic, and you'd get x equals 1, and you get some other value that's an extraneous solution. You get a negative value. So we got x equals 1 as our upper limit for our integral, because that's the, so we got x equals 1, sorry, which it is y equals 1 also, right? If we plug in 1 each of those, so it's actually y equals 1 up there. But we got 2 pi times the integral from 0 to 1 of our radius times our height, dy. And so if we are going to revolve this thing around that line y equals -2, the radius is going to extend from here, where that rectangle is, all the way down to y equals -2. So one piece of that here is 2 units, and the other piece of it right here is just y units. So this time, since we're revolving around y equals -2, the radius isn't just going to be y. Our radius is going to end up being 2 plus y. And our height is just the right bound of this region minus the left bound of this region. So it's just the right-hand function, the 2x minus 1, minus the lower, the left region, which is root x. But because we're doing this in terms of y, and this is an x value, right? That's x, and this is an x value, right? Each of those are x values. We'll call this one x1 and this one x2. Right? x2 is just the x value of 2x minus 1. Well, 2x minus 1, if y equals 2x minus 1, x is equal to y plus 1 over 2. So that's this x2 value. And if y is equal to root x, then x is equal to y squared, and that's that x1 value. So our height is just the y plus 1 over 2 minus the y squared. So we're looking at 2 plus y times y plus 1 over 2 minus y squared dy, right? We got 2 pi. We've got our integral from the lower bound to our upper bound, 0 to 1. We've got our radius, and we've got our height, and we've got dy, our thickness. Here we're talking about the same region. So y equals root x, y equals 2x minus 1, and the x-axis. But this time we're going to go around the line y equals 5. So I'll again sketch the rectangle through here and sketch a shell, cylindrical shell, a hollow cylindrical shell. I didn't do a very good job of that there, but all we really need is enough to give us the info that we know this is dy. and that we can find our radius and our height. And we'll note that the height here of this shouldn't change, right? This rectangle is exactly identical to the one we just did a second ago. So our height is still y plus 1 over 2 minus y squared. And if you change the region that, not change the region, but change the line that you're revolving the region around, the height won't change, right? The height of that cylinder is always going to be the same. The radius is the only thing that's going to change here. So this time our radius extends from the line we're revolving around down to that rectangle. Well, from the rectangle down to the x-axis is y units, and the whole thing is 5 units. So that radius that we're getting there ought to be 5 minus y. So this integral is going to be very similar to the last one. It's going to be 2 pi times the integral from 0 to 1, our lower bound to our upper bound. And now our radius is just 5 minus y. And our height remains unchanged, y plus 1 over 2 minus y squared dy. And again, you can distribute all this out and integrate it all just using the power rule. But the integral setup is the thing I'm most concerned about. So we've got just a few more of these that we're going to take a look at here. So in this case, we're going to look at the equation x equals 12 times y squared minus y cubed. And we're going to try and revolve this around the x-axis. And so if we do this, here's our x-axis, right? If we're going to revolve this region around the x-axis, what we would do is we'd sketch a rectangle that's parallel to the axis we're revolving around, which puts this in terms of y, right? That's got a thickness of dy. And so we would note that if we tried to revolve this around the x-axis and slice it vertically, we would do it in terms of x. But it's going to be really difficult for us to solve 12 times y squared minus y cubed for y, because, and even if we were able to do that nicely, we would note that this thing is not a function, and that the upper bound and the lower bound of this region, right, the upper bound and the lower bound of it, are defined by the same equation. So we have to split this up into like a piecewise function. It'd be a huge mess solving that cubic gap into terms of x. But doing it using shells is going to allow us to do it in terms of y, which means we're not going to have to change that function around at all. So as we revolve this around our x-axis, we're going to get a cylindrical shell that kind of looks like this. And it's obviously going to start off with 2 pi, and it's going to be an integral from the lower bound to the upper bound. And we can see both those from the graph. There's 0 and 1 of our radius times our height. And our radius here for our function is just the distance from the x-axis up some y units. So our radius is just y. And our height is just x. It's the distance from the y-axis over to the function. And so x is just equal to 12 times y squared minus y cubed. So all we've got is 2 pi times the integral from 0 to 1 of our radius, y, times our height, 12 times y squared minus y cubed dy. And there's our setup. And again, this could be distributed out and integrated. It's just a simple power rule. So we're going to do this twice more here. We're going to first take this same region and we're going to revolve it around the line y equals 1. And if I sketch that rectangle parallel to it, we know it's still going to be in terms of y. And we know that the height of this thing, and our height here, is going to remain unchanged. Yeah? The height of this shell is still going to be the x coordinate, or 12 times y squared minus y cubed. The only difference as we revolve this around here is our radius. And our radius up here is going to be different. Our radius will be the entire distance from the line we're revolving around, y equals 1 to the x-axis, minus this portion that we call y. So our radius will just be 1 minus y. So the only difference in our integral this time, the 2 pi remains the same, the 0 and 1 remains the same. Our radius changes to 1 minus y, and our height stays as 12 times y squared minus y cubed. And our thickness is still dy. No major difference other than the value for the radius. And suppose we wanted to go around the line y equals 8/5 up here. Our integral should remain almost identical. Again, this rectangle that we sketch in here is still dy. Our height is still the same. But our radius now is 8/5 minus this y value. So our radius is 8/5 minus y. And so this integral would end up being 2 pi times the integral from 0 to 1 of 8/5 minus y times 12 times y squared minus y cubed dy. And just for the heck of it, since we haven't done one in a while, and this is the last problem we're going to do for this year, might as well evaluate this one. We can pull the 12 out and make it a 24 pi out in the front. And it'll be an integral from 0 to 1 of, when we distribute this, 8/5 times y squared, it'll be 8/5 y squared. And then we're going to have an 8/5 times the y cubed, so a minus 8/5 y cubed and a minus y cubed when we do the negative y times the y squared. So that'll be a minus 13/5 y cubed. And then the negative y times the negative y cubed will be a plus y to the 4th dy. And we'll integrate to get 24 pi. And then the integral of 8/5 y squared using the power rule ought to be 8/15 y cubed. And then the integral of negative 13/5 y cubed, when we go up to y to the 4th and divide by 4, should give us negative 13/20 y to the 4th plus, and then y to the 5th over 5. And we'll evaluate that from 0 to 1. And as we go through, we know when we plug 0 into each of these y cubed, y to the 4th, and y to the 5th, we're going to get 0. So really all we're looking at is 24 pi. And if we evaluate each of those at 1, we'll get 8/15 minus 13/20 plus 1/5. And 8/15 minus 13/20 plus 1/5 looks like a good common denominator there would be 60. Right? So that'd be 32/60 minus 39/60, and then plus 12/60, which would be 5/60. So we got 24 pi times 5/60. 5/60 is just 1/12, and 24 pi times 1/12 would just be 2 pi. And the units cubed. And that is the end of what we're going to do with cylindrical shells. Just remember, it's a good way to use the opposite variable as you'd use for discs and washers to find a volume. And one little thing to note that I didn't mention here at the beginning, but cylindrical shells are never going to be required of you on the AP test. It's perfectly acceptable if you find a problem where it makes your life easier to use cylindrical shells, but there won't be any problems where you can't also use discs and washers, and they will never specifically ask you to use cylindrical shells. I mean, I think it's important, and your Calc 2 professor next year, if you decide to take calculus next year, will really want you to know how to use shells. They'll expect that you know how to. And so I think it's important that you learn it, and it will be on my test. But it won't be required of you on the AP test. And that is our last lecture for the regular material for AP Calc AB, and we'll spend the rest of the year talking about practice multiple choice and pre-response questions and get prepped for the AP test. But that's it.